It will work better if I take it off mute. Okay. So what I want to do now is I want to just do a programming problem. So we'll do aces up. What was the game called? Yeah, I think it's called aces up. And then we'll do a number of iterations. And then I'm going to say no local variables. I'm going to be lazy, and I'm going to immediately end things. So again, you want to get into good programming habits. So the name of the program should be something reasonable, aces up. And the way this game works is it's a solitaire game. You have 4 piles, and you can always remove a card if there's a card that is higher in that suit already exposed. So a king of clubs can remove a 4 of clubs. An ace of clubs can remove a king of clubs. And you win if you end up with just 4 aces. If you have an empty column, empty pile, you can move any card on the top of a pile there. The problem with this game is if your last 4 cards are in 4 different suits, do you have any way to win? No, because you're going to have the 4 piles filled by then. By this far deck, after we've done 48 cards, you've seen a spade, a heart, a diamond, and a club. So you've got to have 4 piles. So what is the probability that you have your 4 final cards in 4 different suits, in which case, no matter how well you play, you lose? It turns out I think it's around 10%. The calculation is not that bad. How many choices do you have for your first card? Can the first card be anything? Yeah, first card can be anything. So you have 52 out of 52 choices for the first card. So we could even say that, theory, it would be 52 over 52. Now for the next card, what would it be? If you want to get a different suit. How many choices do we have for the next card? So it can't be the same suit as the first card. So how many cards are left? 39. So it'd be 39 out of 52. And then the next card?
Would it not be 51?
Oh, sorry, 51. It would be 51. Thank you. The next card? 26 out of. And then the last one? 13 out of 49. And then I'm going to multiply by 1.0 just so that it's now a decimal and not going to be. Mathematica would keep that exact and give you a ratio of 2 integers, but you don't want to see. What should I have put over here? I should put a comment. Given that we have on the order of 10 minutes left, I'm not going to really do comments right now in the code. I'll just speak it. So we'll let successes equal the number of successes. And then we'll just count how many successes do we have, or do we want to count failures? And this is a philosophical point. We're trying to count the probability we have 4 different cards. Is it a success when we have 4 different cards? Yes.
When we turn in problem sets where you ask us to code,
yes,
do you expect comments in them as well?
It's a good idea to put comments. And also for you, it's just to get into a good habit. We got the clock going. And so, so I'll say, I will put in, because it's important, probability have 4 final cards in 4 suits. And of course, you can do a more general thing where you have more than just 4 suits in the deck, and you can have more than just 52 cards. You can have more than 13 cards in the suit. You could make a more general program like this. But again, in the interest of time, we'll just do the standard deck. So now we need to create a deck. So I'm going to initialize the deck to be empty. And now, what should we choose as the values of things in our deck? We've got the aces, the kings, the queens, the jacks. We have all the different suits. I could use the numbers 1 to 52. Or I could just put in numbers that would be useful. I want to know if I have 4 different suits at the end. So maybe each suit gets a number. What number should I give the first suit? 1. What number should I give the second suit? 2 is a possibility, but there's something better than 2. We've seen it before. 10. What should the next suit be? 100. What should the last suit be? 1,000. So if the sum of your final 4 cards is 1,111, you've got 1 of each suit. And if it's anything else, you don't. So now what I'll do is for I equals 1, I less than or equal to 13, I plus plus, append to deck we'll do j. And then here we should do for j equals 1, j less than equal to, we'll do, I guess, 0, j less than equal to 3, j plus plus. And now instead of doing j, I'll do 10 to the j. End of j loop. So this should give me a deck where I put in first 13 ones, et cetera, et cetera, et cetera. We can test this. Let's put this down here, let's run the code. And now let's print out what deck equals. And so looking at it, you can see that it works. So whenever possible, you always want to test your coding to see, is it doing what it should? I frequently have 2 windows open. I program in far too many languages, and I always forget what is the syntax. So if you have multiple languages, just open up another window. So now we've initialized the deck. So now we have the main loop for n equals 1 and less than equal to numdo n plus plus, and then this is the end of the end loop. So we now have to take a sample. And so what is the command now? So we could do...
Wait, is that num iter?
Oh, yes, am I doing num iter? Thank you. Thank you. So I think it's a random sample. Are people able to see things at the bottom? So random sample deck of size 4. And it gives me my numbers. So what I'll now do is I will call temp equals random sample deck of size 4. So depending on what system you're using, you'll have slightly different syntax. But the idea is choose 4 elements. Okay. And now value is going to equal the sum of temp k. K goes from 1 to 4. So this is going to just sum the elements. And then if value equals what? 1, 1, 1, 1, success equals success plus 1. And I think that should be it. And now print theory. And then we'll just do, I think we called it theory. And we'll do it, we'll make it as a %. We'll be fancy. And then print observed. And it would be success times 100 divided by num iterations. All right. The dangerous moment. Do we think we actually coded it correctly?
I think there's one small.
Okay, good. What did we do wrong?
Like I think when you do the success times 100 divided by num iter, you should do like a 0.0.
I'm sorry?
Do 100.0 so you get that.
Oh, okay, yes, yes. Yeah, okay, good. That is a really minor mistake. So, no, because we actually forced theory to be a decimal by multiplying by 1.0. So they were okay. So now we'll do aces up. Now I should really save the program first. I'm going to do a small value like 2. Because if you run a large value first and the program crashes, it's going to hang up and you'll be in trouble. Run a small value first, make sure it works. Okay, the theory said 10%, we observed 0%. Crap. Theory must be completely wrong. I am so sorry you had to see this today as a visitor. What did we do wrong? I mean, it's not even close, it's off by 10%. What should we try?
Figure.
The larger number.
Oh, larger number. Yes.
Oh.
No, it didn't work. It didn't happen. Let's try 100. Now the observed is still 0. Now that's worrying me. So the question is, so if we go over here, we look at random sample.
Oh, you said for n equals 1 and less than num, it should be num
num
iter.
Okay, there you go. And that should be num iter. Okay, excellent. So if we go back to 2, it's still bad. If we go to 100, now it's 7% versus 10.5%. Are you accepting that? Is it okay? But 1,000. 10.8%. Now the other thing which is nice about Mathematica is I can put a little timing here and get a sense of how long it's taking. So it's basically running so fast it can't even tell me how long it took. So that means I can probably pad in 2 more zeros, and it takes 0.64 seconds, and now we're getting 10.549 for the theory, 10.606 for the observed. If I pad 1 more zero, how much longer should it take? It took 0.64 seconds before. How much would you expect this to take? Oh, 6.4 seconds. Okay, it took 7 seconds. You know, considering how the processors and what else is going on. Wait, you know, just to end on the class, 10.549. That's not bad. And this was not a hard program to write. This is the level of coding I want you to be able to do in this class. You know, simple for loops, sometimes while loops. I want you to have something that you're keeping track of. I want you to be able to do some kind of random sampling. And then I want you to be able to compare, hopefully if we have a theoretical projector, to compare the theory to the experiment. Now, how long should this take to run?
A minute.
Yeah, a little bit more than a minute. You really want to get a sense of what is the runtime. In the operations research, I gave them a problem where you can do up to 5 without any trouble, 6 with a little bit of sweat, 7 is tremendously difficult, and 8 is almost surely impossible with systems that they have. You want to get a sense of, is the cost going to be that much more as you go higher and higher up? We're not storing anything. We're not having big arrays that get larger and larger that we're working with. We're doing a simple count, simple calculation, and then just counting. So this should really end in on the order of a minute. So I know class has ended right now, so you are welcome to, oh, good, thank you, just in time. As we've got 10.5319 versus 10.5498. So again, very close with a quick, reasonable accuracy. Now you could ask, what if the theory was slightly wrong? What if it wasn't divided by 51, but what if it was divided by 52 every single time? How different would that be? So I'll leave that as something else for you to check. All right. Have a great rest of the day.